Hello. In this video, we are going to study the variations of another exponential function. In this function, you are going to see we have two oblique asymptotes and one vertical asymptote. We are going to determine these asymptotes, and then we are going to see how to prove that this function is strictly monotonic or strictly increasing all over the domain. And we are going to see how to find or how to prove the equation f of x equals 0 has a unique solution over a certain interval. And finally, we are going to draw the graph of this function. Let us start with determining the domain of this function. In order to determine the domain for this function, the condition here for this function to be defined is the denominator shouldn't be 0. It means the condition here is ex minus 1 shouldn't be 0. So how to solve this equation? We take 1 to the other side. It means ex shouldn't be 1. Set ln both sides, so ln ex shouldn't be equal to ln 1. So x shouldn't be 0 because ln 1 is 0. So the domain for this function will be df. So x can be anything except 0. So we can take all values, all x except 0. Okay? So it means from minus infinity till 0, open, union, open interval 0 plus infinity. Once I find the domain, the question is to find the limits over the boundary of the domain. So it means I have to find the limit at minus infinity, the limit at plus infinity, and the limit at 0. Let us start with limit as x approach minus infinity f of x. What will this be? So as you can see here, the limit for the first part, x plus 1, as x approach minus infinity, it's going to be minus infinity minus 2e minus infinity, which is 0, over e minus infinity, again it is 0, minus 1. So this will be equal minus infinity minus 0, which means minus infinity. Now the limit as x approach plus infinity, as x approach plus infinity f of x, this will be the first part of the function. As x approach plus infinity, x plus 1 will approach plus infinity, minus 2ex will approach plus infinity, over ex, it's plus infinity minus 1. So we're going to have plus infinity minus plus infinity over plus infinity. Plus infinity over plus infinity, which is an indeterminate form. How to solve this indeterminate form? We may apply Hopital's rule only on this part, okay, on the indeterminate form. It means here, if I apply Hopital's rule, I keep the limit as x approach plus infinity. So on the first part I can't apply Hopital, so I will leave it x plus 1, minus limit as x approach plus infinity. Hopital's rule says that we should find the limit of the derivative over the derivative. So the derivative of 2ex is 2ex, because the derivative of ex is ex times 2 is 2ex. The derivative of ex, it is ex, minus the derivative of 1, it is 0, so we have ex. Hence, solving this, ex and ex cancelled, so the first limit is plus infinity, minus the second limit is 2, so the answer will be plus infinity. Okay. Now the last limit is limit as x approach 0. As x approach 0 f of x, this will be 0 plus 1 minus 2 e0 over e0 minus 1, which is equal to So 0 plus 1 it's 1 minus e0 it's 1 times 2 it's 2 over 1 minus 1. So we get 1 minus 2 over 0. So which means plus or minus infinity. Hence this means the line x equals 0 vertical asymptote. Okay, so this is the first asymptote we may deduce from the first part. Now let's go to the second part. In the second part we have to prove that the line y equal x plus 1 is an asymptote. It means oblique asymptote to the curve c at minus infinity. In order to prove that this line is an asymptote to c at minus infinity, we have to show that limit as x approach minus infinity f of x minus y should be 0. So this limit, I need to prove that the limit as x approach minus infinity f of x minus y of d, of course, should be 0. How to prove this? First, let us calculate this limit. So limit as x approach minus infinity. What is f of x? F of x, it is x plus 1 minus 2ex over ex minus 1 minus y, it means minus into, always after minus open bracket, y it's x plus 1. Okay, so this will be limit as x approach minus infinity of x plus 1 minus 2ex over ex minus 1 minus x minus 1. Hence this is equal x minus x cancelled, 1 minus 1 cancelled, so it is the limit as x approach minus infinity of minus 2 ex over ex minus 1. So obviously as x approach minus infinity, so this will be 0. Okay, 0 over 0 minus 1, which is 0. Since the limit is 0, therefore the line d of equation y equal x plus 1 is an oblique asymptote at minus infinity. Now the second part of the question is to study the relative position between c and d. Relative position between c and d, it means which curve is above the other, c above d or c below d. So in order to determine whether c above d or c below d, first we have to study the sign of f of x minus y. F of x minus y, which we already found here, it will be minus 2 ex over ex minus 1. So as you can see here, this is f of x minus y. Now as we can see here, I need to study the sign of this part. In order to study the sign of this part, we need to study the sign of the denominator, because the numerator we have ex always positive times minus 2, it's always negative. So we know the sign of the numerator, it's always negative. Remain to study the sign. So what determines the sign of f of x minus y is this part, okay, because this part always negative. So let us try to find the sign of the denominator. First, I set this table. This is x, this is f of x minus y. Now we set the domain. The domain was minus infinity 0, we have z at 0 vertical asymptote, and plus infinity. So to determine the sign of ex minus 1, if I try a value greater than 0 here, 1 for example, and I substitute 1 in x in this expression, we are going to have minus 2 e1 over e1 minus 1. So if I calculate this expression, obviously this expression will be negative by calculator. If I calculate this using a calculator, we are going to get a negative value. So it means on this side of the domain we will have a negative f of x minus y, whereas if I try a value less than 0, for example negative 1, we are going to have a positive value here. So in this case we have c above d, and here c below d. So this is the relative position between c and d. Let's go now to the next part, which is we have to prove that the line d prime with the equation y equal x minus 1 is an asymptote to c at plus infinity, which is quite similar to the previous exercise or previous part. If I calculate, we have to calculate the limit as x approach plus infinity in this case, f of x minus y of d prime. We need to prove this limit equal to 0. Let us simplify this limit. Let's see what we get. As x approach plus infinity, f of x, it's x plus 1 minus 2 ex over ex minus 1 minus of x minus 1. So this will be equal limit as x approach plus infinity. So x plus 1 minus 2ex over ex minus 1 minus x plus 1, which will be plus x minus x cancelled, so it will be limit as x approach plus infinity of 2 minus 2ex over ex minus 1. So if I find this limit, this will be equal to the limit of 2, which is 2 minus 2 minus limit as x approach plus infinity of 2 ex over ex minus 1, which will be equal to minus infinity over infinity, right? Because e plus infinity is plus infinity. So we have here indeterminate form. We should apply Hopital's rule for this term, and this will be equal, applying Hopital's rule, we keep the 2 minus limit as x approach plus infinity. Derivative of 2ex is 2ex. Derivative of ex minus 1 is ex. So cancelling ex and ex, so we get 2 minus 2, which is 0. Therefore, d prime, which is y equal x minus 1, is an oblique asymptote at plus infinity. Now, to determine the relative position in this, so the second part of the question is the relative position between c and d prime. Now, again, we have to study the sign of f of x minus y of d prime, which means f of x minus y of d prime, it will be this expression, okay? So this will be 2 minus 2ex over ex minus 1. Now, common denominator, so this is 1. Common denominator, it is ex minus 1. So we get 2 times ex minus 1 minus 2ex, which is 2ex minus 2 minus 2ex over ex minus 1, which is equal to 2ex minus 2ex cancelled, that is minus 2 over ex minus 1. Again, similar to the previous part, the numerator is always negative, so what determines the sign is ex minus 1. So let us set this table. This is x, this is f of x minus y d prime. So domain minus infinity, 0 plus infinity. So if I try a value greater than 0, which is 1, for example, we get substituted here, okay? So we get minus 2 over e1 minus 1, which will be negative. If I calculate this using calculator, so here negative, this side positive. So here c above d prime, and here c below t prime. Let's go now to the next part. In the next part we have show that f is strictly increasing function and set up the table of variations of f. In order to prove that the function f is strictly increasing, we should prove, or we should show that the derivative of f is strictly positive for all values of x. In order to prove that f prime is strictly positive, let us find f prime. So what is f prime? F prime of x, the derivative, this is equal. First, if we recall the function we have is given by, so f of x, which is x plus 1 minus 2 over ex minus 1. So in order to find the derivative for this function, first the derivative of x plus 1, obviously it's 1. We have minus here, so we put minus. The derivative of 2ex over ex minus 1, this is of the form u over v. So as we know, the derivative of u over v should be u prime v minus v prime u over v squared. So let us apply this. So if we go down again to part 3, so f prime, the derivative of x plus 1, it's 1, minus the derivative of 2ex, it is 2ex, this is u prime, so 2ex, it is 2ex, times v, which is ex minus 1, minus v prime, the derivative of ex minus 1, it is ex, times u, which is 2ex, over v squared, it means over ex minus 1 squared. So let us simplify this. This is equal 1 minus 2ex times ex, it is 2x 2ex times minus 1, it's minus 2ex, minus ex times 2ex, it is minus 2e2x. Over ex minus 1 squared. So this will be 2ex, 2e2x minus 2e2x cancel. So this is equal 1 minus times minus, so we have minus here and minus here, minus times minus is going to be 2 plus 2ex over ex minus 1 squared. And this means that f prime of x is strictly positive for all x in the domain, because 1 is a positive number. We are adding to 1 2ex, which is always positive for all x, and over this 1 square, it's always positive. So 1 plus positive over positive, which is strictly positive for all x in the domain. Hence f is strictly increasing over the domain. To draw the table of variation of f, so let us draw the table of variation of f. We have, this is x, this is f prime, this is f. Domain, it's minus infinity, 0, plus infinity. At 0 we have vertical asymptote. F prime, we proved that f prime is always positive. It means the function f is always increasing. So we proved that the limit as x approach 0, f of x will approach infinity. So here we have increasing, it means here it's increasing to plus infinity, and starting from below and increasing should be from minus infinity. Now at minus infinity here, as x approach minus infinity, we proved that the line D of equation y equal x plus 1 oblique asymptote, and it's from minus infinity also. And as x approach plus infinity, it was plus infinity, and the line D prime of equation y equal x minus 1 is an oblique asymptote. So this is the table of variation of f. Now in part 4 we have to show that f of x equals 0 admits a unique solution alpha over the interval 1.5, 1.6. To prove this, we should apply the intermediate value theorem that says, first, our function f is continuous, right, over the domain. And f of 1.5 equals to 1.5 plus 1 minus 2 e 1.5 over e 1.5 minus 1, which is equal to, using the calculator, this will be minus 2 e 1.5 divided by e 1.5 minus 1, which is equal to minus 0.07 minus 0.07, which is negative, and f of 1.6, it's going to be equal to it's so it's 0.09, which is positive. Hence, f of x equals 0 admits at least one solution in the interval 1.5, 1.6. I need to prove that this solution is unique. We say f but f is strictly increasing, hence this solution is unique. Let's go now to part 5. In part 5 we have first to verify that 2 over ex minus 1 equal minus 2 plus 2ex over ex minus 1. In order to verify this, I'm going to start with the right side and prove it equal to the left side. Let us start. Minus 2 plus 2ex over ex minus 1 is equal to common denominator, so it's going to be ex minus 1, so it's minus 2 into ex minus 1 plus 2ex, hence this is equal minus 2ex plus 2 plus 2ex over ex minus 1 minus 2ex plus 2ex, this is equal to 2 over ex minus 1. and that's what we have to prove. Now if we go to part B, in part B we have to show that minus alpha is also a solution of the equation of x equals 0. We already have proved before in the previous part that alpha is a solution for f of x equals 0, right? So here in the previous part we proved that alpha is a solution for f of x equal to 0. It means f of alpha is equal to 0, right? We need to prove now in the second part 5b, that minus alpha is also a solution. How to prove minus alpha is also a solution for this equation? It means we have to prove that f of minus alpha is equal to 0. How to prove f of minus alpha is equal to 0? Let us calculate f of minus alpha. We have f of minus alpha, it's minus alpha plus 1. So let me recall f of x. What is f of x? F of x, it is x plus 1 minus 2 ex over ex minus 1. So f of minus alpha is going to be minus alpha plus 1 minus 2 e minus alpha over e minus alpha minus 1, which is equal to minus alpha plus 1 minus 2 over e alpha over 1 over e alpha minus 1. So let us find the common denominator in the denominator. So this is minus alpha plus 1 minus 2 over e alpha over the common denominator here, it is e alpha, so it is 1 minus e alpha. So outer times outer over inner times inner, or you may cancel e alpha and e alpha here. So you get equal minus alpha plus 1 minus 2 over 1 minus e alpha. Now we can write this minus alpha plus 1 minus 2 over minus into e alpha minus 1, which is, if you multiply this minus with this minus, we get minus alpha plus 1 plus 2 over e alpha minus 1, which is equal so if you go back to here, we have proved that in this part that 2 over ex minus 1 equal minus 2 plus 2 ex over ex minus 1. So this means, what is 2 over e alpha? 2 over e alpha minus 1. This can be written as minus 2 plus 2 e alpha over e alpha minus 1. So let's write, instead of 2 over e alpha minus 1, it will be minus 2 plus 2e alpha over e alpha minus 1. So instead of 2 over e alpha minus 1, this will be equal minus alpha plus 1. So this is plus 2 over, right? So it's going to be minus 2 over plus minus 2 plus 2e alpha over. Okay, so minus 2 plus 2e alpha over e alpha minus 1. So this is equal minus alpha plus 1 minus 2, it is minus alpha, okay, minus alpha 1 minus 2, it's minus 1 plus 2e alpha over e alpha minus 1, which is, if I take minus common factor, it will be alpha plus 1 minus 2e alpha over e alpha minus 1. And now this is equal to minus, this is f of alpha, right? and we already know that f of alpha is 0, so minus alpha minus f of alpha is going to be minus 0, which is 0. So we proved that since f of minus alpha is 0 also, hence or therefore minus alpha is also a solution for f of x equal to 0. Now they ask you to find a framing for minus alpha. We already know a framing for alpha. How to find a framing for minus alpha? So we start by setting alpha between 1.5 1.6. So if I multiply by minus, it's going to be minus 1.6 less than minus alpha less than minus 1.5. Hence, minus alpha belongs to the interval minus 1.6 minus 1.5. So this is the framing for minus alpha. Let's go now to the last part, which is we have to draw the graph of this function. In order to draw the graph, first, before we draw the graph, I need to recall the table of variation. This is x, this is f prime, this is f, minus infinity, plus infinity. We have vertical asymptote at 0, f prime always positive, positive, increasing, increasing. So here plus infinity, minus infinity, here plus infinity, minus infinity. So here we have line D of equation y equal x plus 1 oblique, and here we have line D prime of equation y equal x minus 1 oblique. Now, as we have here the x equals 0 vertical, it means the y-axis is vertical asymptote. So we draw it as a dotted line. This is x-axis, this is the y-axis, this is 0. So in order to draw the oblique asymptotes, we should take this table. This is x, this is y. We take particular points on the oblique asymptote. If I take x0, y is going to be 1. If I take y is 0, x will be minus 1. So 0, 1, minus 1, 0, these are the points on the first vertical, the first oblique, sorry. 0, 1, this is 0, 1. Minus 1, 0, this is minus 1, 0. So this is the oblique asymptote. This is the line D. Now we have the second vertical oblique asymptote, sorry. This is x, this is y. If x is 0, y is minus 1. If y is 0, x is 1. So 0 minus 1, this is 0 minus 1. And 1, 0, this is 1, 0. So this is the second oblique. This is line D prime. So these lines are parallel since they are with the same slope 1. Both have the same slope 1. So to draw the graph, here according to this table of variation, the graph starts from minus infinity of the oblique and goes up to plus infinity of the vertical. Now it means the graph will go from minus infinity of the first oblique, which is line D. From here it goes up till plus infinity the vertical asymptote. It should cut the x-axis. Now, as in part 5, we proved that f of x equals 0 admits another solution minus alpha, and minus alpha is between minus 1.6 and minus 1.5. So this solution, this is minus 1, so my solution minus alpha should be somewhere here. Okay, so this is minus alpha, so the graph goes from minus infinity of the oblique till plus infinity of the vertical. So it cuts the x-axis at minus alpha, and second part of the curve, it goes from minus infinity of the vertical till plus infinity of the second oblique. From minus infinity of the vertical, this is the vertical, minus infinity of the vertical till from here it goes till here. of course it will cut the x-axis at another alpha, which is between 1.5 and 1.6, so alpha somewhere here. So this is the second part of the curve. If I want to check or to draw this curve again using GeoGebra, which will be more clear, so as you can see here, so this is the graph. So the curve cuts the x-axis at A with abscissa minus 1.54, and at another point B, which is with abscissa 1.54. So we have y-axis vertical asymptote, and these are the two obliques. Okay, so this is a much clearer curve. So this comes to the end of this video. Thank you very much, and see you in the next videos.